We always hear about making AI models bigger and bigger, but what if the real bottleneck isn't their size but the very task we're asking them to do? Well, there's a new paper out called Calm that completely rethinks this, tackling a core inefficiency that's been hiding in plain sight. Let's dive in and see how they pulled it off.
It's no secret, right? Today's language models have scaled to just, mind-blowing levels. Their ability to understand and generate text is incredible, and they're powering everything from our search engines to some seriously complex creative tools.
But here's the crazy thing. Underneath all that power, every single one of them, from the tiniest to the most massive, is built on the exact same foundation, predicting text one single token at a time. And that, as it turns out, is a huge, huge bottleneck.
And this slide right here, this shows you the whole game. On the left, you've got the old way, this slow, step-by-step process of predicting just the next token. But on the right, that's the Calm approach, predicting an entire vector, which is basically a compressed bundle of a whole bunch of tokens. It's kind of like the difference between typing out a message one letter at a time versus generating whole phrases at once.
Okay, so let's really dig into this. Why is this whole token-by-token thing a problem? It's been the standard for years, but as these models get bigger and bigger, the cracks are really starting to show.
And honestly, this quote from the paper just nails it. We're using these ridiculously powerful billion-parameter models, and we're giving them a task that hasn't changed one bit. It's like we've built a Ferrari engine, but we're forcing it to drive in first gear, just predicting these simple, low-information chunks one by one. This table really puts some hard numbers to that mismatch. A standard token, you can see, carries a pretty small amount of information. Think of it like a single word part. But a continuous vector, it can be scaled up to carry way more information, like 4 times as much, kind of like a complete phrase. And what that means is the model has to make way fewer predictions to generate the same amount of text, which, well, that's the secret to its speed.
And this brings us to the core concept of the Calm paper. It's all about leaving this old world of discrete, one-at-a-time tokens behind and learning to think in these rich, continuous vectors.
So here's the basic idea. First, the system grabs a chunk of tokens. Second, a special tool comes in and compresses that whole chunk into a single, super information-rich vector. And finally, the AI's only job is to predict the next vector. By doing this, it just drastically shortens the sequence it has to think about, which makes everything way more efficient.
So, what is this special tool? Well, it's something called an autoencoder. You can kind of think of it like a universal translator for the AI. It learns to do 2 things perfectly. The encoder part squishes a chunk of tokens into a vector, and the decoder part expands that vector right back into the original tokens.
Now, here's the absolute key to this whole thing. The translation has to be almost perfect. If you lose information when you compress and decompress, the whole system just falls apart. But the autoencoder they use in Calm, it achieves over 99.9% token-level reconstruction accuracy. It's basically lossless, and that's what makes this entire approach even possible.
Okay, so now that we have the core concepts down, let's look under the hood. What does the Calm architecture actually look like when you put all these pieces together?
From a high level, it's a really elegant, continuous loop. First, it compresses a chunk of input tokens into a vector. Second, the main model predicts what the next vector in the sequence should be. And third, it decodes that predicted vector back into tokens, which then become the input for the very next prediction step.
At its heart, CALM still uses a transformer, the same powerful engine that's behind most of today's language models. The huge difference is what it's actually processing. Instead of single tokens, it's now chewing on these information-dense vectors. So its job is to look at the sequence of vectors it's seen so far and make its best guess about what vector should come next.
Now, this is where things get really clever. The transformer's guess is fed into this special component that acts kind of like a sculptor. See, because it's working with these fluid, continuous vectors instead of a fixed vocabulary of words, it can't just pick the next token from a list. It has to actually construct the next vector from scratch, shaping it into what it thinks is the most likely continuation. And finally, to close the loop, that newly sculpted vector gets passed back to the autoencoder to be translated back into normal text, into regular tokens. And this is a super critical step because it grounds the model, making sure its predictions still follow the rules of actual human language. Without this, the model could just drift off and start making up nonsensical vectors. These new tokens are then fed right back into the start of the loop, and the whole cycle begins again.
So the architecture is brilliant for sure, but it all comes down to one big question. Does it actually deliver on that promise of being more efficient?
So, after all that complex engineering, did it actually work?
The answer is a huge, resounding yes. A COM model managed to get comparable performance to a traditional model while needing 44% fewer flops. And flops are just a direct measure of the computational work needed to train a model. We're talking about a massive reduction in cost and energy here.
This table right here, it really tells the story. Just focus on that LLM model. It gets a Breyer LM score of 5.72. And remember, lower is better here, so it's actually outperforming the baseline transformer. Now look at the cost. It did this using almost half the compute power, the train flops, so you're getting better performance for significantly less work. This just opens up a whole new frontier for efficiency.
So what does this all mean for the future of AI? Because let me tell you, the implications here go way beyond just this one model.
The key takeaways are basically threefold. First, it's just ultra-efficient by its very design. Second, and this is the big one, it introduces a brand new way of scale these models called semantic bandwidth. And third, because it works so differently, the paper also gives us a whole new toolkit for training and measuring these kinds of models.
And here's why that matters so much. For years, the path to better AI has been this two-lane highway. Just add more parameters or add more data. COM gives us a third dimension to scale along. We can now improve models by increasing their semantic bandwidth, the amount of raw information they can process in a single predictive step. It's a completely new and powerful lever for building more efficient and more capable AI. And that leaves us with a pretty fascinating question for the future, doesn't it? We've been so focused on building bigger and bigger models. But what becomes possible when we can also build smarter models? Models that scale not just by brute force size, but by the richness of the very concepts they process at every single step.